I now call to order the Society's 2507th meeting and the annual President's Lecture in what is now the 153rd year since its founding on March 13th, 1871. Good evening, everyone. My name is Larry Milstein. I'm the president of PSW, one of the oldest scientific societies of Washington, D.C., committed to providing a forum to further scientific understanding and inquiry. Welcome to our members, guests, and friends to tonight's PSW meeting and the lecture by Javier Garay on fusion energy meeting the engineering challenges. Tonight is the occasion of the annual President's Lecture, and we honor the event by using the Society's ceremonial gavel, hewn from timbers of the White House, used in its rebuilding in 1816 after it was burned to the ground by the British in the War of 1812. Keep in mind that enemies can become friends. According to the brass plaque, the wood used to make the gavel was recovered from the White House in 1927, not when it was rebuilt during the administration of Harry S. Truman, which is what I used to say. Some of the wood from that refurbishment was turned to paneling that now adorns several White House rooms as well as the gavel. And we're pleased to have this small connection to the nation's history to uphold the tradition of using it to call to order the annual President's meeting. Just a reminder of who burnt our White House down. The Society is grateful to PSW Full Year Series sponsors, PSW member Mike Helton and Helton Associates LLC. Thank you, Mike. And to series sponsor PSW member Joe Schulman, who's not here, but thank you, Joe. And to the sponsors of this particular lecture, PSW members Robin Taylor and me, Larry Milstein. PSW has been given a generous donor match, 2-to-1. Every dollar you give gets $3 for PSW from now through January 31st. So please give now if you're going to give. And if you're not going to give. We are going to be matched up to $10,000, so this match is worth a total of $30,000 to us. So please look in your wallets and see if there's anything left after inflation and taxes, and think about giving us a few bucks. I'm pleased to announce that we have 2 new members of the General Committee. Will Blair, a newly elected member at large. He is a software engineer with SpaceX. And Illy Wonder. She is a naval architect with the Coast Guard. We welcome both of them and thank them for contributing their time, their effort, and their expertise to PSW. Thank you both. I'm pleased to announce the following new members. Eric Wargotz, a physician interested in pathology, oncology, genetics, and genomics and public health, who learned a PSW on the web. Harry Stein, a retired physician broadly interested in science, particularly astronomy, who learned a PSW through the PSW Meetup Group. Ethan Virgil, a software engineer with SAP National Security Services, interested in computer science, particularly biometric data storage, machine learning, and natural language processing, who earned a PSW online. Joanna Porter, a financial management analyst with the Navy, interested in the history of science, astrophysics, and the design of space-based instruments, who learned a PSW from YouTube. Christopher Agpaoa, a student member studying law, interested in physics, especially gravitation and exotic matter, who learned a PSW from Google. And tonight's speaker, Javier Garay, who learned a PSW from our invitation to speak tonight and whose interests will be clear in a small part, at least, from tonight's lecture. We welcome them to membership. All members entitled to a signed copy of Volume 1 of the Bulletin of the Philosophical Society of Washington. If you haven't received yours as a new member, please come see me after the meeting. Please also note that members of the Society are entitled to attend dinner with the speaker. There is a reception and dinner with each speaker before the lecture. It is a very enjoyable time to spend with other members of the Society and to get a chance to talk to the speakers. And that is one good reason to join. If you're interested in joining, you can do so via the homepage at www.pswscience.org. There are cards in the back of the room. If you don't remember that, they have QR codes, so you don't have to remember anything. You just have to use your phone. You go to the homepage in the upper right-hand corner. There is a blue join button. It's very distinct. Click on that and follow the prompts. Fill out a form, pay dues, and unless there's something seriously wrong, like you're a felon, you probably will be elected to membership. Well, that was an unintended joke. Sorry. Recording Secretary Scott Matthews will now present the minutes of the 2506 meeting and the lecture by Joanne Hewitt on particle physics and the P5 report.
Thank you, Larry. Good evening. On December 6, 2024, members of the Society and guests joined the speaker for a reception and dinner at 5:45 p.m. in the members' dining room at the Cosmos Club. Thereafter, they joined the other attendees in the Powell Auditorium for the lecture proceedings. In the Powell Auditorium of the Cosmos Club in Washington, D.C., President Larry Milstein called the lecture portion of the 2506 meeting of the Society to order at 8:07 p.m. Eastern Time. He began by welcoming attendees, thanking sponsors for their support, and announcing new members. Scott Matthews then read the minutes of the previous meeting, which included the lecture by Jun Yi titled The Nuclear Clock, Scaling Quantum Systems for Precision Metrology. The minutes were approved pending a minor correction. President Milstein then introduced the speaker for the evening, Joanne Hewitt, director of the Brookhaven National Laboratory. Her lecture was titled The Science Driving Particle Physics and Big Accelerators. The speaker began by presenting an image of a single event at the relativistic heavy ion collider, the result of a collision between two gold ions, showing the shower of hundreds or perhaps thousands of individual particles detected after such a collision. She indicated that this was the level of complexity associated with accelerator experiments, tracking the energy and momentum of each particle produced in the collision. Hewitt went on to describe some of the basic ideas and terminology of particle physics and accelerator experiments. She described how interactions in quantum field theory can be represented by Feynman diagrams. She presented the standard model of particle physics, including a table of 16 fundamental particles and the mathematical equation describing the interactions between these particles. Hewitt described some of the outstanding questions about the standard model. Quote, what is the purpose of the second and third generation of particles? Why is the top quark so massive? How do quarks and gluons behave inside a proton? End quote. The speaker then presented a brief history of the Higgs boson, how it was predicted, how it was discovered, and how the science of particle accelerators enabled its discovery. She described how the Higgs was observed in the LHC at CERN by observation of its smallest decay mode, decay into 2 photons. Hewitt explained that while the confirmation of the Higgs was the final piece in the standard model, several big questions remained, particularly the questions of dark matter and dark energy. She stated that, quote, when you receive an answer to a question, it often leads to further inquiries or new areas of exploration. Hewitt gave a list of several outstanding questions in particle physics, including, why are there so many kinds of particles? What is the nature of neutrinos? What stabilizes the mass of the Higgs? Why is there more matter than antimatter? Are there extra dimensions? Do the forces unify? The speaker presented some of the details of the 2023 Particle Physics 10-year strategic plan, including the 3, quote, science drivers it identified. These included decipher the quantum realm by revealing the mysteries of the neutrino and the Higgs, explore new paradigms in physics by searching for new particles and new quantum phenomenon, illuminate the hidden universe by determining the nature of dark matter and cosmic evolution, Hewitt then presented a list of 25 specific experiments recommended in the 10-year plan, several pre-existing, several currently under construction, and several planned for the next decade. She indicated that some of these experiments were, quote, smaller scale, requiring relatively small investments, and several were, quote, huge colliders that are multi-billion dollars. The speaker gave details about some of these experiments, including a near-term upgrade to the LHC, a number of near-term experiments on dark matter and dark energy, a near-term domestic facility for neutrino experiments, a far-term offshore Higgs factory, and a far-term multi-TeV collider. Hewitt discussed some of the fundamental questions about neutrinos, including the Majorana nature of the particle, the mass hierarchy, the existence of sterile neutrinos, and possible CP violation in the neutrino sector. She discussed the search for dark matter, including the 36 order of magnitude mass spectrum, the use of quantum sensors, the search for WIMPs, weakly interacting massive particles, and the irreducible background due to solar neutrinos. She discussed the search for dark energy, including the Rubin Observatory in the Atacama Desert, which will acquire high-resolution images over a period of 10 years. And last, she discussed upcoming collider experiments, including increasing the luminosity of the LHC by a factor of 5 to 7, an electron-ion collider under construction at the Brookhaven National Lab, and an international accelerator facility still in the planning stages, possibly to be constructed in Japan, which may be either a linear collider or a circular collider. Hewitt briefly discussed the advantages and the disadvantages of these two collider configurations. Hewitt ended her talk by saying that it will require a broad suite of experiments to probe and unlock the secrets of the universe. The lecture was followed by a question and answer session. A member asked if there were plans for collaboration between CERN and Brookhaven. Hewitt responded that Brookhaven is already the U.S. coordinator for collaborations at CERN's ATLAS detector, and that CERN has already agreed to participate in several aspects of the electron-ion collider at Brookhaven. A member asked whether there were plans for a muon collider. Hewitt indicated that muon colliders were relatively far in the future, but that one of the experiments listed in the 10-year plan was, in fact, capable of creating muon collisions. She estimated that such a collider would not begin construction until about 2040 or 2050. A guest asked about the plausibility of cosmological theories that did not include dark matter or dark energy. Hewitt responded, quote, "I have not yet seen a paper that was plausible all the way through from start to finish," end quote. A viewer on the live stream asked whether supersymmetry had been ruled out by TeV experiments at the LHC. Hewitt responded that this was a complicated question and that there were several ways that supersymmetry could hide at the LHC. She said that while there is no evidence that has been found for supersymmetric particles at the current energy range, they could exist at higher energies just outside the range of the LHC. A member asked Hewitt to predict which experiment would produce the next big result in the field. Hewitt responded, Rubin. After the question and answer period, President Milstein thanked the speaker and presented her with a PSW rosette, a signed copy of the announcement of her talk, and a signed copy of Volume 1 of the PSW Bulletin. He then announced speakers of upcoming lectures, made a number of housekeeping announcements, and invited guests to join the Society. He adjourned the 2,506th meeting of the Society at 9:35 p.m. Eastern Time. Temperature in Washington, D.C., minus 0.5 Celsius. Weather, fair. Audience in the Powell Auditorium, 46. Viewers on the live stream, 46, for a total of 92 live viewers. Views of the video in the first 2 weeks, 677. Respectfully submitted, Scott Matthews, Recording Secretary.
Thank you, Scott. Terrific job. Really appreciate it. Are there any comments or corrections to the minutes? Hearing none, I'll entertain a motion to accept the minutes as read. The second. All members in favor? Aye. All members opposed? The minutes are accepted unanimously and will be posted to the website in due course, subject to any comments that come in or online. We now turn to tonight's lecture by Javier Garay on fusion energy, meeting the engineering challenges. Javier is the founding director of the UC San Diego Fusion Engineering Institute and professor and associate dean for research and professor of mechanical and aerospace engineering in the Jacobs School of Engineering at UC San Diego. He leads the AMPS lab doing research on advanced materials, particularly on engineering the micro and nanostructure bulk materials. The lab also develops and maintains capabilities for measuring materials properties so that there is a seamless interplay between materials design and evaluation of actual properties and performance in devices. One of the lab's focuses is understanding the relationships between the length scale of nano and microstructural features on the light, heat, and magnetic properties of materials. The lab's work aims overall to lead the way to next-generation optical and magnetic devices and energy storage materials, among other things. Javier is an author on numerous scientific publications on materials science and engineering. Among other honors and awards, he served as chair of the Materials Science and Engineering program at UC Riverside, was the recipient of 2 Young Investigator Program Awards and an Faculty Early Career Development Award from NSF. He earned a BS in Mechanical Engineering and an MS and PhD in Materials Science and Engineering at UC Davis. Without further ado, all questions will be fielded at the end of the lecture during the Q&A session. Javier, the stage is yours.
Thank you, Larry. And thank you, everyone, for being here. It's a real pleasure and a real honor to get to tell you about some of our work. And of course, is the work of many people. I'll say that in the beginning, and in the end, I'll show you some of those people who have contributed to these ideas. So this is the outline for the talk. We'll start with the motivation and background for fusion energy. Then I'll tell you about 2 breakthroughs that we think are really leading the way and giving us renewed hope and optimism for fusion becoming an energy source. Then we'll switch and talk a little bit about the engineering institute that we have for fusion that we have started at UC San Diego. And then we'll run through some of what I think are some of the major engineering challenges that we need to overcome so that we can have fusion energy on the grid. And those will be materials for fusion. Then we'll talk about the fuel capsule, or we call the target designs for energy. And then finally, the fuel production. We have to produce half the fuel, and I'll tell you why that is and how people plan on doing that. So just a little bit about the background, right? So fusion really is exciting. It really offers potential for nearly limitless carbon-free energy, excuse me. Importantly, it's always available. So it's a grid-based, firm fixed source. And if you were somebody providing energy, let's say a SDG&E or someone like in California like that, you would want your energy to be always available. You want it to turn on when you need it and to turn off when you need it. Then the fuel is also abundant, and we'll talk about that. Half the fuel is available from seawater. It's also considered safe, and again, it's a carbon-free source. So why fusion energy? We talked a little bit about some of this already. It's a baseload grid level scheme. It can have a small footprint. So people are talking about future fusion power plants being the size of large stores. So nothing much larger than that. There's a large increase in demand for energy, right? We hear about this all the time. So some of the drivers are worldwide economic growth. We have, of course, the electrification of vehicles. And then these 2 that have come more recently on the scene. So artificial intelligence has drastically increased the demand for energy. And it's poised, according to Goldman Sachs and others, to really increase a lot in the next coming years. The economics. So, of course, economics is always a driver for technology. And Bloomberg here has estimated that fusion could be a $40 trillion industry. So that's a driver. There's always competition for new technologies. And we must keep in mind that fusion should be cost competitive with other renewable and other types of energy as well. So for these kind of things to be a reality, it must be cost competitive, and that's where some of the engineering challenges come into play. So let's talk about some of the physics, some of the basics here. So this is I took this slide from a good friend and colleague Mike Campbell. And Mike is an avid cartoonist, so we have our friend Albert Einstein here saying that, of course, E equals mc squared, turning light and energy into matter is a good idea. So I'll talk about this reaction that's, so explain fusion from this most commonly considered reaction. So hydrogen, like the most common form of hydrogen, like most of the hydrogen that is in this room, is one proton, one electron. Now, if you add a neutron, you get something called deuterium. So now you have a neutron and a proton in the nucleus. You add two neutrons, and now you have tritium. So what if you could provide enough energy, enough power, pressure, enough temperature, and hold it long enough so that you can fuse these two hydrogen isotopes together? What you would get is one helium atom, a helium-4 atom, called alpha particle, and you would get a neutron. So the alpha particles serve to further heat the plasma. We'll talk about the importance of plasma. And the neutrons are the energy carriers outside of the reaction. These neutrons are what we have to capture for useful work. Okay, so here's a little different type of illustration. Let's say you have this super tanker. The amount of water that this super tanker displaces, you can get about 40 liters worth of deuterium, half the fuel. So this deuterium is naturally occurring in the seawater. The other half of the fuel, the tritium, you have to breed, and we'll talk about how some schemes for tritium breeding. Then you take these two fuels and you can fuse it, and it's no coincidence that we're using the sun as an analogy. Of course, fusion is the power source of the sun and the other stars. And then that fusion reaction with those 40 liters would produce as much energy as all of the oil that's in that tanker. And importantly, you wouldn't have to emit all that carbon dioxide that you would otherwise emit. So that's the promise, and that's the excitement there. So how are people doing this, and how are people thinking about these things? Well, there are two ways. I mentioned plasma. You need to confine the plasma for some time at a given pressure and a very hot temperature. And there's two different ways of doing that. But there's really not much of a mystery of why it needs to be a plasma, right? Because this is a very high energy reaction that needs to take place. Now, if I go to the opposite side and I remove all the energy from something, let's say I go down to absolute zero. So if I go to absolute zero Kelvin, 0K, I've removed all the kinetic energy from matter. So all the energy that's left is just the internal energy because it's matter. If I heat it a little bit, add a little bit of temperature, those atoms will start vibrating, but they're still solids. If I heat it more, of course, they become liquids. And if I heat it more, it becomes a gas. Give it more energy, and that reaches the fourth state of matter, of course, which is plasma. What's interesting about a plasma is in that state, the atoms can no longer hold on to their electrons. They become ionized, so now you have ions and electrons. And that is important because that plasma is now high energy, but it also can be controlled with electromagnetic waves, right? And this is exactly how this magnetic confinement fusion takes advantage of the ability to be able to control the plasma with the magnet. And that's how you do it. There's a picture here of the central core of the D3D, which is in San Diego. It's a national fusion facility operated by General Electric. So you can imagine this person standing here the plasma is not on, obviously, but if one were to control plasma and swirl it around here, you can continuously add energy. Like I mentioned, because the plasma is conductive, you can keep adding energy until you get some kind of reaction that you would like. On the other hand, another way that you can also confine the plasma is using something people call inertial confinement fusion. This is a picture here of the National Ignition Facility. at Livermore, California, operated by the Lawrence Livermore National Lab. So in addition to these federally funded user facilities, there are now fusion experiments that are going on in public companies. So this is two examples. On the magnetic MFE side, we have Commonwealth Fusion Systems in Boston, and in Tokamak Energy in the UK and other places. And on the inertial confinement side, we have Exemer Energy based out of Colorado and Pacific Fusion, just some examples there of these two different schemes. So why now? Well, I'm going to tell you a little bit more in detail, but really after decades of investment, about really over 50 years, 5 decades of investment in the US, mostly from the Department of Energy, there have been two key technological advancements, and we're calling breakthroughs here, that drive the huge re-emergence of interest. One was the at Lawrence Livermore National Lab at the NIF that I just showed you, demonstrated ignition for the first time in December 2022, and we'll talk about that. We'll talk through it. The second part, the second breakthrough is that magnetic confinement devices are now being built with superconducting magnets, and we'll talk about why that's important. So with this excitement, there's been a lot of investment. So there's $8 billion, for example, in the last few years in private investment in fusion companies. So let's talk about the first breakthrough, ignition. So the laser was first demonstrated in 1960 by Theodore Maiman at Hughes Research Lab in Malibu, California. And very soon after that, John Knuckles at Livermore suggested an inertial confinement scheme to compress heat and confine a plasma, so the birth of the IFE idea, the ICF idea. Interestingly, and coincidentally, John Knuckles received the Fermi Presidential Award from the DOE this year, and I think his award was just presented today. So the NIF was completed in 2009, and after a couple, 14 years or so here, on December 5th, on 2022, ignition was first achieved. What that means is that more energy came out of the fusion reaction than was put in by the laser. Okay, and this is how we'll talk a little bit about how that happened. But this schematic here of the NIF is showing a building. So the NIF is about size of about 3 football fields on end, and it's 10 stories high. So it's a very, very large laser. It's the world's highest energy, largest laser. It has 192 beams. It's all concentrated here. And here's a picture of the lasers face all into a point into a vacuum chamber. This vacuum chamber and all the lasers are now focused on this, what people call a target. This is a picture here of a hole ram target that's used in that ignition experiment. And what we see is there's 2 holes here, and the lasers are focused on either side of that hole ram. And then the fuel pellet actually sits here in between and inside this hole ram. Now the fuel pellets are actually very small. So this one here is about the size of a peppercorn, the one that achieved ignition. And here's a picture in front of someone's eye to give you the scale. So imagine a peppercorn that's filled with fuel, deuterium and tritium, and now these 192 lasers impede on it and cause that fusion reaction. It was a really amazing feat, and give you a little bit more of a background here. So the paper that described this here is called it's called Achievement of Target Gain Larger Than Unity. And again, I was showing you this hole ram, and here's the schematic of the lasers coming in. They come in on both sides at different angles, and those lasers turn. This is a gold-coated hole ram, and the lasers cause X-rays to form inside the hole ram, and those X-rays now ablate this target. So here's the target, a little bit more detail about the target. So the high energy X-rays now ablate, remove material from the outside of the target, and that target now, because of the opposite reaction of the ablation, has like a rocket effect, compressing the fuel inside. The fuel is actually the deuterium and tritium is actually a frozen ice of DT fuel around the inner core of the sphere here of the capsule, and some gas of DT in the middle. And here's some data that actually came out of two different experiments. And well, this curve here marked a P is the laser power. So you can see the laser power increases, and what follows is a temperature increase. Now that temperature increase is huge, and you see the temperature that was recorded during the shot. Is here in the hundreds of EV, right? So there's millions of degrees Celsius, right? Very, very hot. So importantly, this has now been repeated 5 times. So ignition has been repeated 5 times since, and the highest gain, the original experiment showed gain of about 1.5, so 1.5 times more energy came out than was put in, and now the highest gain is about 2.36 at the whole RAM level. Actually, at the target level, it's more than 10. So you're getting gain of more than 10 inside this target. Okay, so very exciting, and that's giving people a lot of interest there. The second breakthrough I want to talk about has to do with superconducting magnets for MFE or magnetic confinement devices. So this is some data here out of a 1987 PRL paper by Wu et al. And it's about high temperature superconductors. In this case, it was yttrium, barium, copper oxide, a mixture of yttrium, barium, copper oxide. And what we see here on this plot, this is resistivity versus temperature. And what we see is as you lower the temperature, the resistivity goes from pretty low to extremely low. And this is, of course, a transition to superconduction. So this why yttrium, barium, copper oxide is one example of a family of materials that collectively are now called rare earth barium-containing copper, or REBCO. So interestingly and importantly, these superconducting magnetic coils can deliver a substantially more electric current than typical coils. And of course, by putting current through a conductor, you get a magnetic field. So what this allows is to get a significantly higher magnetic field that can again confine that plasma in now a much smaller place, in a much smaller scale, because you can put more current through these magnets and have a much higher magnetic field inside this coil. So you saw the other picture I showed you before with the person inside. This is another one. So this work here has been done through what was called the SPARC toroidal field magnetic coil experiment, and again in Boston, but with a company called Commonwealth Fusion Systems that we already talked about. They demonstrated in 2021 high field of 20 Tesla, which is a very, very large magnetic field in a small space. Okay, and that is a second breakthrough that's giving a lot of hope that people can now reach gain here. So the SPARC tokamak that they're building is designed to achieve the physics energy gain of over 2. Okay, so that's an exciting proposition that's going on. Okay, the breakthroughs have driven investments, and now we want to go from the scientific breakthroughs that we just showed and technology breakthroughs to really, can these ideas for fusion lead to an actual power plant? Right. So this is some illustration here of the investments. So in red we have the number of companies that are coming online, and there's more now worldwide, more than 40 companies working on fusion. And those companies have gotten a lot of investment. I mentioned in the last few years, $8 billion. There's missing here in 24 because it stopped here in 23. Pacific Fusion got an investment of almost $1 billion just last year. Okay, so now what I'll do is I'll switch gears a little bit and talk about UC San Diego, my home institution, and talk about the fusion history, heritage, and future at UCSD. So UCSD has a long and impactful history in fusion research, and I'll tell that very briefly here based on the work of two fusion pioneers. The first, Marshall Rosenbluth, who was professor of physics and really known affectionately as the Pope of plasma physics. He was affectionately known as because of his overall understanding of plasma physics, particularly in plasma instabilities and also fusion. The second person is Professor Bob Kahn, who was a professor and dean of engineering from 1994 to 2002. He was a very impactful dean, and he brought a lot of rejuvenation of fusion engineering, particularly to UCSD. His NAE citation reads for pioneering contributions in the field of fusion engineering, fusion plasma analysis, and fusion reactors design. Bob is still very much an influential and important person in our fusion program. So today, UCSD performs almost $2 billion worth of sponsored research. That's easily top 5 in the country. And the highly ranked Jacobs School of Engineering is one of the largest schools of engineering, both by students and by research expenditures in the country. And we have nearly 10,000 engineers. So with this heritage of fusion, and the fact that we now realize it's a very hard problem, but a very impactful problem, and we know we have a lot of motivated, very motivated, hardworking students. We want to give them fusion as something to be able to work on. So we're reinvesting. Just one more thing about historical fusion programs. This is an example of the Ares program that had the mission and the goals really to demonstrate fusion power to be safe, clean, and economically important. It was a really one-of-a-kind program that had UCSD led, but it had many universities, national labs, and companies that came together. That's a historical program. And one trend and really take-home message I want to make here at this point and kind of continue as a theme throughout the talk is that fusion is a very hard problem. It's a very important problem, as I already talked about. But no one university, nor one national lab, nor one company will be able to make it on its own. So it's very important that we collaborate. And knowing that, in September 2023, we invited some of the fusion interested researchers from the UC system. The UC system also includes the campuses and the UC run national labs, Los Alamos, and Lawrence Livermore National Labs, and also Lawrence Berkeley. So we did that, and the idea was we wanted to assess both the strengths of the UC system, and importantly, is there an appetite and a want to, again, reinvest and follow this. And I have to say that it was an overwhelming yes was the answer to should we continue contributing to fusion research. Here's a couple of pictures. But at the first workshop, we had members from 8 campuses come, the Office of the President, National Labs, the Department of Energy, and some very trusted and good startup companies and established companies from the private sector. This is a follow-up workshop that we had just last month in December 2024. So with that momentum and that interest, we decided to launch the Fusion Engineering Institute in October 2024. The founding members include 20 PIs, with expertise in both magnetic and inertial confinement. We have expertise in plasma physics, material science, supercomputing, AI, ML, amongst other things. We're in the process of hiring 2 new faculty members. We already have about 30 to 35 PhD students that are working on fusion-related ideas, and we're planning on significantly increasing that, and also importantly, to offer curriculum at the various educational levels. Okay. So with that, I'll turn to some of our engineering challenges, and I'll start with materials for fusion. So here we'll start with the list of the requirements. So I already talked briefly about the very high temperatures and pressures that are needed, right? So the materials for a plasma-facing components, this is more on the magnetic confinement side, and for future fusion devices, are going to be subject to really extreme conditions. right? They have large plasma particle and heat fluxes. The temperatures in the walls there are going to be over 1500 Kelvin. Going to have electric currents. Currents can cause a lot of issues. And importantly, high energy neutrons. We'll talk about why the neutrons are so important and can be so detrimental to materials. And those materials should, in the face of these very harsh environments, they should have a low erosion rate. So we shouldn't remove a lot of material in these harsh environments. They should have a low surface morphology change, right? We can't have a lot of displacements moving those materials around. They should have low vapor pressures, so they're not emitting particles into the plasma and causing problems there. They should have low retention of the hydrogen isotopes. You can imagine if your fuel is retained within the material, you're no longer burning it, and it's not a very efficient device. Should have low activation by neutrons. Again, small degradation of, because the neutrons can cause degradation of physical properties, as we'll talk about. And lastly, they should be compatible with other important fusion materials like lithium. Okay. So another theme of this talk is we'll consider not just the materials and their composition, but also how they're made. Importantly, their microstructure. Their microstructure is very important. So here's a schematic that I borrowed here from a review article by Jaime Marian at UCLA. And we on this axis here we have time scale. On this axis we have length scale. So if we start here at short times and short and small length scales, the first things that happen under exposure is you start getting a lot of defects generated. As you have longer length scales and time scales, you start trapping some of that fuel. So the fuel that I was talking about. Even longer length scales and time scales, you start having major changes to the microstructure. So for example, and I'll show you some other micrographs of this, but you can have void formation. You can have the diffusion and major microstructural changes. And of course, what happens when you do that is that material that you started with is no longer the material that you engineered to start with. So one thing that can really happen is that material now becomes brittle, and the fracture toughness goes way down, and now your material will break when you don't need it to. And of course, that breaks your device. Okay, so here some other micrographs again from Professor Marian's review article, and this is some examples of microstructural variation under various irradiation conditions. And this is a phase diagram. So what we have on this axis here is there's temperature, and on this one is the irradiation dose. So how much exposure to neutrons? If you're a materials person, you're familiar with phase diagrams. Often what's shown is temperature and pressure, right? But in this case, we want to show temperature and neutron dose because it's the neutrons that are important there for the material changes. So at low temperatures, you see here the microstructure. If I go up in temperature, what starts happening, just like I mentioned before, is you start getting a lot of defects that are generated. And the defects that are generated are so-called dislocation loops. So you start getting these loops of dislocations, changing the microstructure. If you go up to very high temperatures at kind of low doses, you start getting void formations. Void formation is very bad for the material. Because if you know something about fracture mechanics, what controls fracture in a material is the flaw size. The fracture toughness goes as 1 over the square root of the fracture, of the length scale of the fracture. So if I have a larger void, it acts like an initial crack, and you're going to crack that material. So a large void formation is a major problem. If you look over here, on this side, at larger doses, you get not just the dislocation loops and the voids, like we already talked about at these lower doses and higher temperatures, but we also start getting some precipitates formed. And this is for a relatively pure tungsten material. So these precipitates are caused actually by transmutation, the material changing because of the neutron exposure. So tungsten transmutes, changes to a different element, to other elements near tungsten like osmium and others, and those different elements, as they diffuse around the matrix, cause these precipitates to form. Those precipitates are again a problem because your material is no longer the material that you started with, a major problem. So to learn a little bit more and to think about ways that we might be able to address these problems, I want to take a step back and talk about atomic diffusion in general, because atomic diffusion is really the what controls phase evolution, phase changes, and therefore the material performance. And typically, when we think about diffusion, we think about the temperature, right? So KBT energy dominates. Boltzmann constant times temperature is the energy that dominates. But again, in a fusion reaction, the material exposed to fusion reaction, the fusion neutrons and ion surrogates, a lot of experiments are done with ion as surrogates, you can have athermal atomic displacements. So the atomic displacements that are not caused by temperature, but are caused by the neutrons impacting on the material itself. If we want to write an equation here about this, is the diffusivity, which controls how fast the atoms can move in the solid. And what you see here, this is an exponent, and we see that the diffusivity increases exponentially with temperature. So the hotter you get, you're dealing with an exponential response to how fast those atoms are moving. What we have here in the numerator is the energy required for moving the atoms. We call it the activation energy. So the activation energy is where all the material's properties are hidden. So if you know something about the activation energy to move atoms in a certain material, then you can start using those things for design. And that depends on the diffusion mechanism as well as the material, like I was talking about. And this energy can further be thought about as an activation energy is the sum of the energy required to move a defect plus the energy required to create that defect. Okay. Let's move on and show a little bit of schematic here. So for a vacancy mechanism, like in this, if I have a crystal structure of a typical metal, like gold or aluminum, it's face-centered cubic, and I want to move an atom from one part of the crystal to another part of the crystal. This is in 3 dimensions. In 2 dimensions, the most common way that would be done is through a so-called vacancy mechanism. You have a missing atom here, and then an atom moves over, and this is the activation energy that we were talking about. Because this atom has to squeeze in between this smaller volume, you have a low energy site here. You have to supply that activation energy. Typically, this is temperature that supplies that energy, but it can again be supplied by something like a neutron. Okay, so this energy allows the atoms to move, and now you're again at an equilibrium site. This is an interstitial mechanism, and this is important because interstitial sites are always there. So it's always very easy to move amongst these interstitial in-between equilibrium atom sites. And this is how hydrogen moves in metals. So again, hydrogen is the fuel. So in those sites are always there. So that's a vacancy mechanism, a diffusion mechanism that you should consider. So this interstitial diffusion is important when solid atoms, again, are smaller, like in the hydrogen case. Okay. So what's a way that you might be able to reduce diffusion, reducing phase transformation, and making a material, for example, become more resistant to phase transformations? Here's one possible solution. This is out of a paper talking about what people call high entropy alloys. And the idea is that by having a lot of different types of atoms, you no longer have just one single activation energy. You have this rugged energy landscape that makes it more difficult for the atoms to move around. Now, if we were able to design materials with a proper energy landscape, then perhaps we can decrease the diffusion and increase the lifetime of the performance of the material. Okay, so that is one tool we might be able to use. This is a lot of data here out of a very interesting paper just last year that took a modeling approach to screening. And what they did was they used a first principles density functional theory calculation to screen through a lot of materials for data that's already there in the polling file and database. And they went through a lot of various materials, oxides, carbides, borides, metals. And what they did was they said, well, we know a lot about these materials. We know their crystal structure. We know their, and therefore their electronic structure. Let's do calculations so that they can specifically screening for two different problems, namely sputtering, so how much material can possibly come off, and the other is incorporation of interstitial hydrogen, so how much hydrogen might be able to be trapped, and we talked about why that is a problem. So the crystal structure and the related properties, again, are extracted are extracted from the database, and they use the heat loads that are comparable to a tokamak to get that. And what they did here is they presented the screening. Sorry about the small font, but they found some materials that are possibly going to be very good for plasma-facing components, and some that are not so good. Okay, so that gives a tool there to help for screening. A couple comments. So this is a very nice work. It gives some very nice direction. One thing that hasn't been considered here is the microstructure. So it's the crystal structure, but it doesn't talk about the native defects that are already there. It doesn't talk about how the materials were made to begin with. And that's something that we're going to have to do in addition to this kind of modeling work. But really the modeling and experiments in synchronicity is really going to be important. Okay, I'll show you a little bit about why microstructure is so important. And we talked a little bit about mechanical properties. We'll turn to thermal conductivity as an example for why microstructure is important. So the thermal conductivity, written here as K, can be thought about and calculated from the product of three different things. The heat capacity, so how much heat carriers you can move, how much heat you can move with a given carrier. The group velocity, how fast you can move that carrier, and the mean free path, how long that carrier can go before it scatters, before it changes direction. And you have 1/3 because you're thinking about space in 3 dimensions. So how far you can go before you change directions, how fast you go, and how much energy you're carrying with you. So what I've done here is I've plotted thermal conductivity versus temperature on here of 3 materials, all with the same crystal structures. So they're all diamond cubic crystal structures. We have carbon, silicon, and germanium. And surprisingly, we can understand everything that's on this plot, all this curves, with just this simple equation here. Okay, so the thermal conductivity goes to 0 when you go to very low temperatures, and that's of course because the kinetic energy goes to 0, like I was talking about before. Now, as you go increase temperature, your thermal conductivity increases because your heat capacity increases. This is a rise here. Then at some point you get a decrease in thermal conductivity, and that's because your mean free path decreases. You start getting scattering because you have more and more vibrations of the atoms, and they start scattering off each other. And finally, the magnitude, so why diamond is a higher thermal conductor than silicon and germanium, can be understood by the last thing, which is the group velocity. So diamond the atoms can travel the fastest, can vibrate the fastest in diamond. So they have this high group velocity. So it's the highest thermal conductivity. Silicon is heavier, so the vibration is slower. So you get the silicon in the middle. And the heaviest element here is germanium, having the heaviest and lowest frequency phonons, and that's the lowest thermal conductivity there. Okay, so that still doesn't take into account microstructure. So let's put in the microstructure. So if I have a material with large crystals, like large crystal size like this, then the scattering, that mean free path, how far I can go before I change directions is long. Now, as I put in more boundaries or more grain boundaries, I start increasing the number of scattering sites because now the materials the phonons are now scattering off of those interfaces. The mean free path is shorter, so your thermal conductivity is lower. So again, when you when you expose materials to neutrons or to high energy sources, you change this microstructure, and you can change something like a thermal conductivity, which is very important to the properties that you're looking for. So some micrographs here just to show you some data. These are some materials that are made. This is silicon, all silicon with large crystal sizes. Here to small crystal sizes, and these are materials with voids in them, right? Like the voids we were talking about before. So now if I plot that same plot, thermal conductivity versus temperature, the data I showed you before, considering just the crystal structure, is way off the chart here. The material with the real microstructure, the thermal conductivity is much, much smaller. In fact, if I decrease the grain size by a lot, I can decrease the thermal conductivity by orders of magnitude, and if I put voids in, I'm decreasing the thermal conductivity by several orders of magnitude. So again, this material is very different. Even though I haven't changed the composition, it's pure silicon. I haven't added or decreased the different types of atoms. I've only changed the microstructure. Okay, so how can we now take all of this and look for ways of designing a material, and really a material that can withstand those high energy environments? It really is going to take a combination of material synthesis, processing, characterization, and performance and modeling, and we're going to have to do this sequentially so we can find phase diagrams like the one I showed you, but we're going to have to do it for all the materials that are possible contenders, and then down select from there. Now, again, keeping track of the microstructure is going to be key. So one possible way of doing this, and I'm showing here a work by the Pisces group at UCSD, led by George Tynan. And what this test bed does is a newly built test bed, is it allows simultaneous exposure of plasma to high flux ions. Again, ions can be neutron surrogates. So now you can use a machine like this to expose materials that you make under these simultaneous plasma and ion conditions. You can see you can afterwards characterize the performance and start making phase diagrams like the ones I showed you. So you can down select materials and do this iterative design cycle. So finally, you have a material that has a chance to withstand those harsh environments like I was talking about. Okay, so another engineering challenge. Engineering challenge number 2 is fuel capsule target design. So the hologram, the experiment I showed you before done at NIF, used a hologram that looks like this. Now, that it's an exquisite piece of engineering. Took decades to design and build. It's very, very precise. And the NIF fires one shot. You get one fusion reaction. You collect the energy. Excuse me. You look at the energy. You don't collect it. And again, it's done one shot at a time. Now, if we were going to do a power plant and use this for useful energy, you can't have a very exquisite design like this where you shoot it just once. So it has to be made significantly cheaper, much faster, and you have to be able to shoot shot after shot after shot. Okay. So how might you do this? And I'll use this slide also to show some of the real interdisciplinary nature of what it's going to take to do this to make the fusion energy a reality. So again, you can shoot in an energy scheme. You would shoot a capsule in. It would have to be injected very quickly into the chamber. Then you shoot it here with the laser. Then you get the fusion reaction, and then you need to shoot another one. Right, that to making sure that you can hit the capsule, the target, you need control systems because you need to be able to track the target, and you need to be able to make sure to track the target and aim the laser. If you have optics that are close to the reaction, you need to make sure that you get a mitigation of optical damage. And then the targets themselves are going to be micro nanostructured materials, very likely. You need to design those. They're going to have coatings. And of course, you need to deal with all the thermal and energy management. After each shot, you have to be able to clear and get the chamber ready for the next shot. You might use robotics to do that, and you definitely would want to use robotics to maintain and prepare and maintain the chamber for long-term use. So you see all these disciplines that are going to be necessary: material science and engineering, mechanical engineering, electrical, robotics, nuclear engineering, a lot of different uh, um, um, uh, disciplines that are going to be needed there. Okay, so some of the materials that are being considered and some of the some pictures here. These pictures are courtesy of General Atomics. So the capsule materials and the size and the geometry makes a substantial difference on the ablation, so how the material ablates and therefore implodes. And of course, the size does make a difference. So we have some capsules here from small to large capsules. So why, we'll talk a little bit about why the NIF, going back to the NIF shot, why some of the choices were already made and some of the choices that would be needed to make going forward. So this is the data I showed you before. So recall this PRL paper. And you might notice a time scale here in the sort of tens of nanosecond, 10 nanoseconds. Okay, and why that length scale? Why that time scale, excuse me? Well, it turns out that time scale is very important for how much pressure you can get. And to illustrate that, I'm showing you some results here from an experiment we did at the Omega EP facility scale laser. And we were shooting silicon here. So this is some silicon material, which impinged on the laser. And here are the results of the pressure that was caused here at this interface. Here's the position. So as the pressure, the shock wave moves from the surface here through the silicon. And you see is each curve represents a different time scale of the laser that of the laser pulse that was used. So it's at short time scales in the less than 1 nanosecond, you get a very high pressure, but it's not nearly as high as you can get as you increase and make the laser pulse longer and longer and longer. So with the longer pulse, here in the sweet spot, about 10 nanoseconds, you get a very large pressure. And that's why people use nanosecond pulses for these ICF schemes. Okay. Another way that you can get high pressures is by choosing different materials, like I was talking about before. So again, this going back to this data, here's pressure and temperature on this axis, power and temperature on this axis, and here's time on this axis. What you might notice is that when the power of the laser was started, it's not all added at once. So here's the power. It's not all the power isn't delivered right away. As high, the peak power is not delivered immediately. Instead, it's ramped. And the reason why it's ramped is to get, again, the highest pressure and the highest temperatures needs to be done judiciously. And one way that one can do that is by changing material densities. So here's results in some experiments which we had aluminum on one side of a material, of an impactor is made out of aluminum. On the other side is tungsten. Tungsten is a very dense material, very, very heavy. Aluminum is a much lighter element. So if you take this material stack here and you shoot it very quickly, very fast onto another piece of aluminum, the results here, because of the increase of density across the material, the results show this is the backside, the velocity that you're measuring here. The velocity goes up very quickly, but as the material starts to go from aluminum up through tungsten, you get this nice ramp here, just like you do in this ramp. This is for temperature, but you get the same thing for pressure. You get an increased pressure, and that's another way of controlling. So you can imagine as you start to make targets designed for and fuel capsules designed for fusion energy, some of the choices you would make is what density of materials you would use and how they're structured. And I can show you a little bit more about this. This is some nice results out of Livermore in which they 3D printed targets. Now, 3D printing, in this case, 2-photon polymerization, is very exciting because it might be a way that can be developed to print targets very quickly and very cheaply. And what they were doing here is they wanted to make a target that was a higher density on one side and a lower density on the other side, so they can get this increased ramp like I was talking about. And the way that this is architected has different scales here. So the unit cell here is this 4-bar truss structure. Then you take that 4-bar truss structure with less than a micron length scale. So this is a 5-micron bar here, and this is the top view of this. So it's a nanostructured, microstructured truss. And you take that and you repeatedly print that unit cell, and you repeatedly print it again. And so it's a very small target. Here's a picture on a US penny. And what they were showing, they shot this material in some high energy lasers. They shot it in Omega and the NIF. And what you see is this increase, the change in densities drives plasma pistons such that you can get the pressures that you're looking for. So going forward, if people were to make these targets, again, much cheaper and make a lot of them, you would need to use advanced manufacturing techniques, probably just like this. So another way to do it, another example of 3D printed targets. This time, this is work out of Los Alamos, again using 2-photon polymerization, and this we start to see the capsule design. So this is one capsule design that they use they call the revolver ignition concept. So we have different materials. Some of this material, the ablator shell is a beryllium. Then you have secondary copper, and we have inner gold shells. And then in here, they're placing this 2 pp polymerized nanostructured material to hold the two spheres apart. Here's another scheme, very similar but different ideas. In this case, we can see the 3D printed material much clearer. So this is the outer ablation shell. There's 2 halves. In between, there's the 3D printed material. Okay, so these are the starts of 3D printed materials being shot at these big lasers. Again, going forward, this might be one way that we could manufacture materials capsules at scale for fusion energy. This is just some pictures of ultra-fast material printing and processing at UC San Diego. Also working on that. And also want to talk just very briefly about joining materials. Because as we need to engineer materials, we need to have different types of materials, for example, metals and ceramics. And this is just a scheme that we pioneered to weld ceramics. So laser joining, ultra-fast lasers to weld ceramics in air. Here's some pictures of a scheme that we can protect electronics using ceramics, because ceramics, of course, are irreplaceable on many demanding applications, many high temperature, high pressure applications, and typically a lack of an in-atmosphere room temperature joining procedure really limits the use of ceramics, these high temperature materials. But if you can join them, which now we were able to with the laser in air, you can really increase the applicability of these ceramics. Okay. So going back to the target injector and designs, I mentioned you have to shoot a lot of pellets, a lot of these capsules. You shoot them with the laser. Now you have to shoot them in another one. People think that the frequency of injection will be about 10 hertz, about 10 times per second. You shoot the capsule in, you shoot it with the laser, and then it's ready for the next one. There's already been some work. There's some work here courtesy of General Atomics So you can use a gas gun approach or a linear induction accelerator. You also, there's been work on target tracking and laser pointing, and these are the kind of engineering ideas that you would need so you can get this this capsule is designed for laser work to be able to translate to an energy source. So the last engineering challenge that I want to talk about is the tritium breeding and also thermal management using cooling. So I mentioned that half the fuel, deuterium, is available in nature. Tritium is not. So this isotope, there's not enough of it available. So one needs to create it. And one needs to be able to do it within the power plant itself if it were to be a self-sustaining power plant. And how might you do that? Well, you have to think about the tritium fuel cycle, and you have to so-called breed the tritium. So recall, again, the fuel is deuterium and tritium. And an example here, we can talk about tritium breeding using lithium and fusion neutrons. So if you have a burning plasma, you have these neutrons that are naturally occurring, like I talked about before with this DT fuel. Now, if you have a so-called breeder blanket, and that's lithium containing, these neutrons, these high energy neutrons, can now react with the lithium, giving you an alpha particle, so there's a helium-4 again, and tritium, and some energy. So with the same reaction in which you get the fuel, you're burning the fuel, can give you half the rest of the fuel, and now ready to be self-containing. Okay, so that's really the scheme there. So there's people working on this different parts of the world. There's both molten salts that are being considered and molten metals. The most common molten salt is people call FLiBe. So it's fluorine, lithium, and beryllium. And the molten metal is a lead lithium. These are some of the leading candidates. So various breeding blankets have been proposed. In some schemes, the salts and the molten metals are both for the tritium breeding and also as the heat transfer fluid. And in some, they're only for the breeding, and you use a different fluid for the cooling part. This is really an outstanding problem. People are working on this, on how to do this. And one thing I want to stress is that thermal properties will need to be screened for all the materials, and you need to make sure that the materials that you start with, again, are the same materials as you end with after the neutrons. This is some example of why thermal conductivity is important. Of course, thermal conductivity is really important for efficiency of heat exchange. So the hotter you can run your heat exchange, the more efficient your power plant is. And here's some data showing the heat output versus thermal conductivity of the material you use as a heat transfer fluid. So the lower the thermal conductivity, the less heat output you get. And if you're going to design a plant, you want to make sure you know the thermal conductivity, because you need to know how much heat output you can get from the power cycle. And the reason why sometimes that is an issue is some data here. This is thermal conductivity versus temperature of a salt. This is sodium chloride salt, and this is iron. This is molten iron. And what you see here is measurements that are done over the years. And the problem here is that there's a 275% spread between the measurements. And not only that, but there's some measurements suggest that the thermal conductivity goes up with temperature. Some say that it stays flat, and some say that they go down. And now again, I'm just trying to design a plant, and you need to know for sure, and you need to definitely know the temperature response. So again, the heat transfer fluids are going to be really important to know that. So advanced and reliable thermal characterization is going to be necessary for screening, and new flow material compositions need to be screened, especially given at different levels of hydrogen, right? Because the materials are again changing as they uptake and transmute and so on. A possible way of doing this, this is some work out of Renkun Chen's group. that it shows some laser-based radiometry. So now if this is a modulated laser that comes in, and because it's modulated, you can use a thermal model to look at the thermal response, because you get this infrared radiation, and you can now know the thermal conductivity of the material, and you can screen quickly, and you should be able to put a sensor like this, a scheme like this, in a loop where you're getting information not just of the salt or the molten metal as it's made, but also as it performs, right, as it's going through the cycle. This is some work of exactly that, of a molten metal flow loop. This is a lead lithium flow loop that has been designed and constructed at the Idaho National Lab. And it's been specifically constructed to test tritium extraction. So this not only flows the lead lithium, but it also has a tritium extraction part. Okay, and what it's been designed to conform with some of the leading candidates. For example, the helium-cooled lead lithium concept and the dual coolant lead lithium reading blanket. And one other thing I wanted to stress here is how many sections and how many components are in this subsystem. So this flow loop has many subsystems. It has flow meters, it has pressure gauges, valves, heaters, and so on. And the reason why that's important is because it's important to know how all these engineering subsystems will perform with the tritium cycle. Remember, tritium is very small. It can diffuse within those interstitial sites. So the fact that all of these components can work in the face of the tritium cycle is important, because if we don't know if they can work with the subsystem, they definitely won't work in the power in the overall power plant. Okay, so with that, I'd like to summarize. So what we've discussed here is two recent breakthroughs. I told you about the breakthrough experiment done at the National Ignition Facility, showing ignition for the first time. We talked about superconducting coils that are now available for the MFE schemes for next generation tokamaks and other magnetic confinement devices. We talked briefly about the Engineering Institute at UC San Diego. And then we went through three engineering challenges: materials for fusion, fuel capsule target design, and finally the tritium production, the tritium breeder blanket. So with that, I'd like to acknowledge all of my collaborators and colleagues. So of course, students in AMPS labs, collaborators and colleagues at UC San Diego, at General Atomics, and at Lawrence Livermore National Labs. And I thank you again for listening, and thanks very much to Larry, to Dr. Milstein for the invitation, and for all of you for listening. Thank you. I go here.
We have time for some questions. Let's start with the red microphone.
Yes, sir. Thank you very much for this very exciting presentation.
Thank you.
Michael Moore, I am a member, and a long time ago I saw a guy from Westinghouse who worked on a Princeton tokamak drop a piece of stainless on the floor to demonstrate that it shatters like glass. It made me think, wow, we have some engineering issues. You spoke to most of those. Mm-hmm. From a practical point of view, given the state of investment that we have now, what would be your guess when we would have practical solutions to these engineering issues? Thank you very much.
Thank you for the question. So that's exactly right. That demonstration of stainless steel being dropped and breaking because it's brittle, because of all the voids that are formed, is exactly the biggest problem. My answer to how long for practicality, let's say something as practical as a fusion energy on the grid, right? That's probably the holy grail. When would we have? And I think the way to answer that question is it depends, of course, on the resources. You asked, given today's level of investment, I'm going to answer it slightly differently. I'm going to say, well, what if we had a different level of investment? Because what's slowing things down right now, in my opinion, is because of the level of investment that we have, we're not able to tackle things in parallel. Instead, we're having to do things sequentially. If we were able to do more things in parallel and solve these engineering problems and the remaining physics problems of the different schemes in parallel with more people working on it, I think it could be significantly faster than what we're doing. It's a lot faster.
Blue microphone.
Yes, Rich Talbot. I'm a proud member of PSW. To get the neutron flux down, have you guys rejected helium-3 reactions at this point, or are you trying to crawl before you run?
So that's a good question. I think that, so there are, like you're suggesting, I gave an example of the D and the T. So that's that particular DT fuel. There are other fuels like you're mentioning. I think that people are looking at that DT because of previous experience that have been done, and it has a high cross section. So it's practically a reaction that can work at the pressures and temperatures that have been demonstrated and been used. So I don't think anything has been rejected. It's just that the DT is the way that most people are thinking about going right now.
Thank you.
Red microphone.
Michael Albro, member. Impressive progress, a lot of work going on. You gave a materials issue is obviously a very important one. You gave a long list of requirements, another long list of materials being investigated. Is there a nightmare scenario when there's no material that meets the requirements?
There could be, right? But I'll give you a little bit of. So I think although there has been a lot of work done and a lot of materials considered, we haven't had the investment time and in the test beds, especially to test the materials. So I don't think we're near nightmare scenario yet, simply because we just haven't tested enough materials. I'll give you a little bit of an example of from, let's say, the semiconductor industry, right? And you can imagine how long we've been working with semiconductors and how long we've been working with electronics. And still, most of the papers that come into physics journals are still on semiconductor material development today. So I think if we had that level of work and investment on finding the right material, we would. It's just that we just haven't had the resources to do so yet. But yes, there could be a nightmare scenario. One other corollary to that is that there are schemes in which you wouldn't use a solid material. You instead would use a molten material. The molten material would not be subject to the microstructural transmutations and the microstructural problems that I was talking about, and it would just be about how can you flow it, which is still a major engineering challenge, but a different one. So I think that's, if we couldn't find a solid material, we might turn to blankets or do it in parallel.
Thank you.
Blue microphone.
Yes, I'm Federica Derima, and I'm a member. Thank you very much for your presentation. A lot of challenges. And the question is related in terms of materials. What's the role of modeling in selecting materials? And also you had on your list AI, ML methods that have been used, for example, in protein folding for designing new proteins. So you described more or less experimental methods. So where is the role of modeling? Because to kind of go to the example that you gave on semiconductors, there was tremendous amount of modeling that was done for semiconductor design.
Absolutely.
Materials.
Thank you for the question. So I showed very briefly some down selection that was been done with a DFT. So there's a paper that came out last year, very nice paper. What they were looking at there was the crystal structure approaches, so the density functional theory approach to getting the crystal structures, to using the crystal structures to get them to calculate the material properties and then subject them to in that case the tokamak. that is great for screening. What we need more of is the microstructural modeling,
Right.
which is also being done. So there's some nice work done out of Los Alamos National Laboratory and other places that I'm aware of, which you look at also the diffusion modeling, the phase transfer, the phase change, and things like this. And now they're becoming, like you suggested, very, very intuitively. There's AI and ML models that are being added to the physics-based models to increase those calculations. So this multi-scale modeling is absolutely crucial, and it's increasing in use. And like you said, AI and ML is being added to it.
Because you also showed great boundaries, right? And these are a huge kind of factor in terms of the structural aspects of the material.
Yes.
So you need kind of modeling that includes that aspect of microscopy.
Absolutely. And there are some nice grain boundary models, and again, diffusion through grain boundaries, and how the grain boundaries themselves migrate that are being worked on. So absolutely necessary and important.
Thank you.
We're going to go to Matt Kayward on the red microphone, and then we'll take a couple from our viewers online.
Hi, Matt Kayward, member. Speaking of, if you're resource constrained and you can't solve all the problems at once, do we really need to solve the tritium breeding problem, in parallel with all these other problems right now? Because, tritium's got a long lifetime. You can, maybe make it in some other process, although I have no idea. Maybe you can't. But does that need to be part of a reactor design, or is it purely sort of a cost efficiency motivated area of research?
It's a good question. So what you're suggesting is, why not solve some of the other problems and then think about the tritium breeding problem later? In my opinion, I think it should be addressed soon, because I think that the biggest differentiator between the technology demonstration and the power plant is going to be whether you can all integrate it all together. And there has not yet been either an MFE, so magnetic confinement, or IFE approach that tries to integrate the problem. And I think that will be important. I'm not sure if psychologically is the right term, but it's going to be an important breakthrough where you can actually do those two things together. So I think that the tritium breeding should be considered now. It's a choice, but it's my at least that's my opinion.
We'll take some questions from our online viewers, Anne.
Great. Larry, we have 3 questions from the web. The first question is from Paul Hess from Vienna, Virginia. If grid scale fusion becomes feasible, what would the challenges and prospects be for creating smaller scale fusion? Are there ultimate limits for achieving smaller scale?
So that's a really good question. I'm not sure about the ultimate small scale limits. It's really about the amount of power you can get in, right? So let's take that ICF approach. The pellet is already really, really small. It's about the size of a peppercorn. So if one could come up with let's say a laser scheme or another confinement scheme that could deliver enough energy in a smaller volume than today's lasers, then one could theoretically get that fusion energy out of that pellet. So it can be very small, but that's a big if you make the lasers much, much smaller, for example, or the other kind of confinement schemes much smaller. I think that it's feasible to have plants that are pretty small and deployable in small scale cities. And that's part of the attraction. It could be smaller, for example, than a solar farm with storage. So that's part of the attraction.
The next question is from Dave Rabinowitz, who's a member. The question is, in a continuous fusion reactor, how is the resultant helium and for the IC systems the encapsulation material removed?
Yeah, that's a good question. So people call that chamber clearance physics, or so exactly you put the capsule in, you implode it, you get the fusion reaction, and now you have to get the chamber ready. And I've been a little vague about how one might do that. Well, you can imagine differential vacuums where you can have flow and remove the debris. You can do things like that. So some kind of gas flow while still holding some kind of vacuum is a way that one can do it.
Another question from the web is from Gary Thomas, who's a past member from Reston, Virginia. Where will this research go when we think about energy? We can't burn this carbon in space. Will this science lead to clean energy that we can use in our space efforts?
I'm sorry. Could you repeat?
Sure. The question is, where will this research go when we think about energy? We can't burn carbon in space. Will this science lead to clean energy that we can use in our space efforts?
Oh, so could this technology work in space, basically? Yes, this could work in space.
Thank you.
AJ on the red microphone.
My name is AJ Kothari. I'm a member. One of the problems, one of the reasons that you mentioned about need for tritium is actually a problem for molten salt reactor because it creates tritium and it's considered a problem. So and molten salt reactors need neutrons, which the fusion provides. So how about combining these two together to help each other?
That's a very good idea, and people are thinking about that. Just coincidentally, this wraps back into the question that was asked earlier about that is a natural way of getting the tritium. So the tritium could be produced in a fission reaction. I know that there's people that are already. The world's initial supply of tritium would come from the fission industry. So that's one side. Then you could have, like you're saying, a hybrid fission-fusion plant. And some people are talking about that. And that would be an alternate approach to going full fusion. So very, very intuitive, very good question.
Thank you.
I have a question, and then we'll have a question up here, Bob. But my question is this. So ITER's been under construction for quite some time, and it's a very expensive sink for resources. And it was originally conceived before we had these high magnetic flux magnets, before we knew a lot of things that we now know about materials. How much of that actually finds its way into the current construction plans, and how much of this is going to be something built at great expense over a long period of time using technology that's obsolete by the time it's finished?
So that's a good question. I'm not an expert on ITER. However, I do agree with some of those sentiments that I think that different design choices would be made if ITER were to start construction today. And it has been, unfortunate that it's taken as long as it has. I think ITER will still be important from a training ground, experimental side of things. Whether or not it leads to important energy side of things, I'm not sure. And I think
It's an expensive training ground.
That's right. That's very good questions. And I think it's conversations that people can bring up with, various Department of Energy and other people who make those choices.
And for those of you who are interested in the subject, this is the first of 3 expected lectures on fusion. One will be from somebody at DOE, and another one will be from somebody at Commonwealth Fusion. So we'll have hit academia, the government, and private industry. And we should get a good overview of where things are going right now. Red microphone, Bob.
Bob Hershey, I'm a member. Of the various materials you went through, do some of them seem like they're close to optimum of exactly what you need for a fusion reactor?
No, they don't seem like an optimum right now. So that a lot of the choices, at least on the magnetic confinement side, people are thinking of using tungsten and tungsten alloys because they do have tested performance. Whether it's optimum, no, but they're good enough to start with. And in my own opinion, I think some of the pilot plants that will be made, let's say of tungsten or some early materials, will not be the same material. The commercial plants will not be the same materials that the pilot plants are, because we'll have chance to develop new materials.
We'll go to the blue microphone. Maria?
Maria Zamankova, member. Very interesting talk. Of course, all of us want to have fusion, and all of us want it to be, of course, clean and cheap. I was struck by you saying, if I understood it correctly, it's about 1 energy input to 1.5 energy output due to the fusion. And I just wonder what is swept under the rug in that 1. Like, how easy is it really to retrieve the D from the seawater? What happens to the seawater when you remove the D? And of course, tritium has its own problems and all the lasers, etc., etc. So what goes into that 1 to get the 1.5 output?
That's a really good question, and there are a lot of things that are, to use your term, swept under the rug. The most obvious one is the laser efficiencies that I didn't talk about. A partial answer to that is that the NIF is a fantastic laser, but it again isn't the way that you would build the laser for energy. Right? That was a design that had to work. There was a huge investment, and the choices that were made to make that laser work were the choices that were needed to make sure that laser worked, based on decades worth of. There's been advances on laser technology, on diodes, on things that now make the laser side of things much more efficient. You could use different materials again. You can tell my bias here on materials, but to back up a little bit more onto the other things you mentioned, so what about the transportation of the fuel? That's something that needs to be accounted for. But again, it's when you make an efficiency calculation for a power plant, even for coal or natural gas, you don't make the efficiency calculation about getting it there. So the Q, the gain, would not be in that same calculation. The economics would be there. Right, because you do need to spend money in getting the fuel there, so that part of the economics does need to be considered.
But I think the 1.5 was just for the experiment.
One and
We
a
don't
half.
know what we're going to end up with.
Well, it's 1.5 was for the laser in, fusion out, and now it's up to 2.4, 2.36.
One more question from the. Let's do red microphone, Robert. Then we'll do one from the web.
So, Robert Thompson, I am a member. So, maybe following on a little bit from just this discussion, with the inertial confinement fusion at NIF, they use the Hall room as you explained. Mm-hmm. But and then you talked about some of the engineering challenges around making a power plant using inertial confinement fusion. And in that case, you talked about, say, injecting the fuel pellets at 10 hertz and laser tracking and things like that. But one of the big differences is that you don't have a Hall room in that case, right? You have direct drive, where the lasers are directly incident on the target. Yes. And of course, that introduces a whole lot of its own problems, laser plasma instabilities that, don't need to get into all that. Mm-hmm. But I'm just wondering, has anybody done any calculations about the theoretical efficiency of indirect drive versus direct drive, and how does that play into the ignition efficiency, this multiple, right? Of course, because ignition hasn't been demonstrated for direct drive.
Very good. These are great questions. So you're right. In the NIF experiment, had the Hall round, so-called indirect drive. You first laser to X-rays. That's why it's indirect. There's been some really nice experiments done at the LLE in Rochester, the Omega laser, focusing more on direct drive. The difference between those experiments is that the overall power deliverable by the Omega laser is lower than NIF. So we haven't had a one-to-one. So NIF is not designed to do direct drive. You have to have a whole run because of the way the configuration of the lasers. So one cannot do a direct drive experiment on the world's largest lasers the way it's built now. There is talk and about making it so that you could do direct drive experiments on NIF. That would be great, because then you can prove out the direct drive. So there are calculations. I'll tell you, many of the companies that are looking at ICF, IFE, are looking at direct drive. so you wouldn't have a hole around them. You would shoot the capsule. And those are the concepts that I was talking to, is really the capsule would have to be inexpensive, likely some kind of additively manufactured, so that you can have a lot of different materials integrated and done in a cost-effective manner. So hopefully that answers some questions.
We're going to go to the web.
All right, we have a follow-on question from Dave Rabinowitz, who's a member. In fission reactors, moderator materials reduce neutron energy. Are these materials considered to extract energy from high-energy neutrons to reduce damage to other absorbers and containment materials? He continues, even with low thermal conductivity, the energy ends up as heat somewhere.
I'm sorry, could that?
I'll repeat.
Yes.
Yep. In fission reactors, moderator materials reduce neutron energy.
Yes.
Are these materials considered to extract energy from high energy neutrons to reduce damage to other absorbers and containment materials?
I see. So the idea there would be using similar materials used in a fission plant to reduce the neutron flux. I suppose one could do that, but then you would be losing some of the heat carriers. So it would lower the efficiency of the overall plant. Could be done, and maybe if you needed to do kind of an intermediate step, you might be able to do something like that. I think, and generally people think of using all the energy carriers, so use all the flux you can get. But some comments there.
Is that a question back there with the blue mic?
Rich Talbot, PSW member. In the category of expectations management, I've heard a lot of numbers thrown out, like 2030 and whatever. Can you identify what you think is the highest probability technology, and when do you think we're going to crack this problem?
Yeah, this is
I only bring you the hard problem.
yeah.
The crystal ball.
So my own view is that this is not a problem that will be tackled by one single company. So I think that the companies are doing great work, getting a lot of engineering work, a lot of physics work. The ones I'm familiar with, a lot of are making great progress. I don't think that any one company will be able to do it alone. So if there isn't collaboration with academia, with other industries working together to make sure that they solve problems in parallel, I think that's the problem. A lot of the companies that are doing it, for example, aren't thinking about tritium yet. Maybe that's a choice, the tritium cycle, but somebody has to, or else if we don't, then that just gets pushed farther out. I think optimistically, if people were to work together, and there are models for that, and the investment were increased some, it could be pretty fast. So those mid 2030s numbers to me look doable, but with a lot of collaboration, not alone.
Last question from Jared McQueen. Red microphone.
Jared McQueen, I'm a member. Great lecture. I had a question about the logistics of the pellets or the granules. So the targets, it sounds like the timescale for ignition is 10 milliseconds. Would you need a gigantic stockpile of these pellets and to continually run the fusion reaction? And even if you could miniaturize the entire system down, wouldn't you just still need a ton of pellets to continually ignite? And then also, when they're spent, are they waste? And what do you do with the spent pellets? Thanks.
It's all very good questions. Yes, your first part, it's on the order of nanoseconds, so about 10 nanoseconds, maybe hundreds of nanoseconds. And you do need a big stockpile of them, if you would. You can imagine that in an IFE plant, one would have a place where the targets are manufactured, or at least brought into. Then they're filled with the fuel, and then injected into the reactor, right into the device. And you would need a big payload of them, and you would shoot them. You don't have a lot left because it's such a hot. So the waste you mentioned, the waste. you get a lot of particles, small particles that would need to be transported out. But they wouldn't. There isn't a lot. First, of a lot of mass, and then there isn't a lot of. And you get a lot of things that are sort of incinerated very quickly. Right.
You know, you talked a lot about pellets and ICF, but you didn't say anything about tokamak and how do you get the fuel into that? And
That's right.
it's not little pellets for that, I don't think.
No, you need a lot of. So the idea in MFE in tokamak is you would get the plasma going and then inject the fuel.
But what shape does the fuel in?
In gas.
Gas. Yeah. And so then you have all the instability problems from that. Yeah.
Yeah.
Okay. All right. Well, thank you very much for this great talk.
Thank you, Larry. Thanks, everyone.
Wait. But before you go, we have a few small tokens of appreciation. One is a framed copy of the announcement of your talk.
Oh, thank you.
Signed by all the members of the General Committee on behalf of all the members. Another is the ribbon of the Society that you can wear in your pell, like I am.
Great.
Which is emblazoned on its side with these 3 bands that are symbolic of the symbol for inductance, which was studied and characterized by the founder of PSW, Joseph Henry, in parallel with Faraday. And then finally we have, and the unit of inductance is, of course, the Henry. And then we have a copy of Volume 1 of the Philosophical Society of Washington, signed by me on behalf of the membership. You'll find in there who founded the society, why they founded it, and an interesting and, I think, useful discussion of the nature of discourse, or what it should be, in scientific society. And with that, thank you so much.
Thank you.
It was very pleasant to meet you.
I appreciate it. Thank you, everyone. Thank you, Larry.
Okay, well, before you go, we're going to have a very brief announcement in view of the weather. Let me just say that the next talk will be by Scott Wolk. He'll be talking on highlights of the X-ray universe, and partly to celebrate Sandra's 25 years of observations, which is this year. Sandra's still up there and still making fantastic observations. The spring schedule is filling in, and here you go. Let me just say again that we hope to have 3 talks on fusion. The other 2 are not in there yet, but sometime in 2025, we hope to hear from industry and from the government on what they're doing with fusion. But as you can tell, there are a lot of problems, and it's going to take a massive effort to solve them. With that, I want to thank our helpers here who ran the cameras and the video. Motion to adjourn? Second? Second. All in favor? All opposed? We are unanimously adjourned to the social hour.